The other area of striking ground deformation is near the Norris Geyser Basin, the hottest and most unstable thermal basin in the park.
Norris Geyser Basin is one of the most dynamic of the hydrothermal areas at Yellowstone. It's always changing. We're always noticing new things that are happening.
Just a few years ago, satellite images showed Yellowstone's greatest rise in this area. Recently, however, it's reversed its direction and is now subsiding.
It's not actually within the Yellowstone caldera, yet it's one of the highest temperature thermal areas in the park. And it is possible that there is some magma extending to the north beneath that region.
The source of the basin's volatility could be magma, or another key component to volcanic activity, earthquakes.
The earthquakes are essentially the heartbeat of the system. They are an integral part of the active, if you wish, mountain building and volcanism of Yellowstone.
Like smoke and fire, volcanoes and earthquakes go hand in hand. The pressure from the magma, which can explode into a volcano, also forces the ground to shift, causing earthquakes. They can be the telltale signs of an impending eruption.
The two main precursors to a volcanic eruption, seismicity and ground deformation, are very carefully monitored in Yellowstone.
In this computer model, each red dot represents an earthquake. Typically, hundreds of earthquakes are detected across the park each year. In recent years, the greatest earthquake activity has been centered under two areas of the park.
Well, you can see we have earthquakes that are concentrated on the north side of Yellowstone, coming down through the park, and then out extending on the east side of the Teton Fault right here.
What concerns geologists is when a center of earthquake activity overlaps an area of shifting terrain. At the Norris Geyser Basin, that seems to be what's happening. There are dozens of fault lines at this spot.
That's very critical because if magma is starting to move up, we would expect to see a bulging in an area and associated earthquakes as the ground starts to crack.
The fear is faults that make up the earthquake zone could crack under pressure from the magma below, releasing an eruption. Geologists are also watching the park's geysers, hot springs, and mud pots, looking for drastic changes in temperatures and chemical content. Anything that might indicate a major movement of magma. At the moment, geologists do not believe an eruption is imminent. But if the water temperatures were to rise, the ground begin to swell, or there were an increase in earthquake activity, another Yellowstone eruption could be building.
I think that we are smart enough as geoscientists now that we would probably have weeks to perhaps months of indicators before anything like that would occur.
However, predicting the precise timing of an eruption is far from simple. Scientists have been fooled in the past.
We've seen it in Yellowstone. There's bulging, there's vibrations, there's increased seismicity. There's all the things one would expect and go, oh, uh-oh, we're in trouble. And then, nothing.
Yellowstone's supervolcano has been hit by a series of earthquakes, with more 30 recorded since June 12. The latest was recorded on Monday, June 19, with a magnitude 3 earthquake striking 8.6 miles north-northeast of West Yellowstone, Montana. The swarm began last week, and on June 15 saw a magnitude 4.5 earthquake take place in Yellowstone National Park. The epicenter of the shock was located in Yellowstone National Park, 8 miles north-northeast of the town of West Yellowstone, Montana. Scientists from the University of Utah, which monitors Yellowstone volcano, said in a statement. The earthquake was reportedly felt in the towns of West Yellowstone and Gardner, Montana, in Yellowstone National Park, and elsewhere in the surrounding region. This earthquake was the largest to have hit Yellowstone since March 30, 2014, when a magnitude 4.8 earthquake was recorded 18 miles to the east, near the Norris Geyser Basin. The 4.5 earthquake is part of an energetic sequence of earthquakes in the same area that began on June 12, the statement continued. This sequence has included approximately 30 earthquakes of magnitude 2 and larger and 4 earthquakes of magnitude 3 and larger, including today's magnitude 4.5 event. As of June 16, 235 events had been recorded. Most of these ranged in the magnitude of 0 to 1, with 5 less than 0. The University of Utah is part of the Yellowstone Volcano Observatory, YVO, which monitors volcanic and earthquake activity in Yellowstone National Park.
Supervolcanoes like Yellowstone could explode suddenly, without warning, without seismic movement signaled as earthquakes. When we think of an explosive volcanic eruption, we imagine it being preceded by earthquakes, by ground swelling, by the mountain venting some hot gas, perhaps even some lava. These are the signs we look for in the inexact science of volcanic predictions. But 2 research papers, published on the very same day this year, say that predicting supervolcano eruptions is even more difficult than predicting the eruptions of regular volcanoes. More on that in a moment. But first, do the events in Yellowstone earlier this year demonstrate changes that may be building toward an eruption?
We did have an earthquake of 4.8 magnitude. Now that is the largest we've had in Yellowstone in over 30 years.
And a couple of months later shuts down a road that's melted because of increased ground temperature. People start to get edgy about an impending eruption. I went to Yellowstone recently, and geothermal activity is everywhere. A reminder that you're on top of a super caldera and magma dome, the largest on Earth.
Frankly, we are just a few miles above some really hot magma. That magma serves as the heat that fuels the geysers and hot springs and fumaroles in the park. It's that engine that allows for the unique things that we see here in Yellowstone.
This is what the melted road looks like 2 months later. Yellowstone spokesman at the time said the road had turned to soup, and that was widely reported, even in the mainstream media. But when I spoke to a ranger there, she dismissed it as simply a bad asphalt job.
That was closed due to melting, the heat?
No, it has nothing to do with that. That was just a couple of days. It was the asphalt was soft. It was actually a bad asphalt job that they had done the summer previous to that.
Okay.
And that combined with the intensity of the sun in the middle of the summer, and that it was in a hydrothermal area, that it just got soft.
Oh, okay.
And they just had to replace it.
So it had nothing to do with an increase in geothermal activity in that area, the ground being hotter, it was just the asphalt, wasn't it?
The asphalt, yeah, it was the combination of those things in that particular spot.
I hadn't visited Firehole Lake Drive when I spoke to her, or I would have challenged what she told me. 2 months later, the road still doesn't look good. But more importantly, Yellowstone spokesman told the press at the time that people needed to stay away from the road because there was a high danger of stepping on seemingly solid soil into severely hot water. Contrary to what she said, Firehole Lake is an active geothermal area, and you can see that the road deteriorates as it comes into proximity to geothermal features. But it's what we've come to expect from government employees at every level: fear for their job if controversy erupts, and contempt for the public's right to know. If it was just a bad asphalt job heated up by the sun rather than increased ground temperature, then why are there other melted paved areas that they've just fenced off rather than try to fix? My suspicion is that the spots are so hot at the moment that they can't fix them. Ground temperature goes up and down with seismic activity in the park.
We see between 1,000 and 3,000 earthquakes a year in Yellowstone. Most of them are so small, nobody ever feels them.
Swarms of small earthquakes that you can't even feel can cause the ground to go through major changes. Look at this area that was once a forest. The ground was a hospitable environment for trees to grow for a long period of time. Then in 1978, swarms of small earthquakes caused the ground in this area to rise to 200 degrees Fahrenheit. It wasn't the quakes, but the heat that killed the trees. So while we may be heading into another period of increased activity in Yellowstone, it's far from the largest activity we've seen since it became a park. Of course, everyone will tell you that it's not if, but when the super caldera blows up.
Now, as almost every part of the Ring of Fire is roaring back to life, the supervolcano Yellowstone seems to be also waking up. It's JT here at X Science again. While the Kilauea eruption in Hawaii is still going on in its 4th month, and there's still no sign of it calming down, Yellowstone is seeming to be coming out of its sleep. Should Yellowstone erupt, it is estimated that almost 90,000 people will be killed immediately, and 2/3 of the United States will gradually be destroyed. Let's put that into a comparison. After 3 months of ferocious activities, Kilauea destroyed an area of 15 square miles. Meanwhile, if Yellowstone erupts at full power, it will devastate a whole area of almost 7 million square miles. Not only the majority of US civilization will be gone, but so will be its ecosystem. Now take a look at this photo. This is a map of the world's volcanoes, and as you can see, all the rings of fire is either red or orange, meaning that the volcanoes there are active. Okay, so where is all the worries of Yellowstone super eruptions coming from? Well, 60 miles away from Yellowstone, a fissure of 100 feet cracked up. These gigantic fissures opened up in the area of Grand Teton National Park, in a wall of rock which is 100 feet long. Tour guides of the park discovered this crack and reported it to the park ranger. This part of the park has been closed down for safety reasons. Now, even though officials say that this is not a sign of Yellowstone will erupt, we all know that they need to calm the crowd down. Because how are we going to tell a country that super eruption is coming and it spells doom for 2/3 of its people and will probably devastate the whole earth as well as nothing can be done about it? Well, of course you tell them nothing and assure them that there is no danger. But with the waking up of all the volcanoes on Earth, as well as the increase in the wobble and seismic anomalies because of the incoming system of Planet X, it is very rational to expect Yellowstone will soon join the list of active volcanoes. What we need to do is keep an eye out and prepare ourselves for the worst. Now I would like to end this video with some more interesting facts on the Yellowstone supervolcano. In the past 2.1 million years, it has gone through 3 super eruptions, namely the Huckleberry Ridge 2.1 million years ago, the Mesa Falls 1.3 million years ago, and the Lava Creek 630,000 years ago. The last eruption I mentioned spilled 240 cubic miles of rock, dust, and volcanic ashes into the sky. Oh, and by the way, the surface of Yellowstone has been rising and its speed is increasing abnormally, so we can expect the worst.
August 1883, Indonesia. The Krakatoa volcano blew itself to pieces, creating the loudest sound in recorded history. June 1991, the Philippines. Mount Pinatubo blasted debris 22 miles into the atmosphere. Suffocating ash swamped over 2,500 square miles. And in May 1980, Mount St. Helens caused $1 billion of damage. The ever-present threat from these volcanoes makes it essential for scientists to understand the forces that power them. The investigation begins here, in Alaska. This land of rugged beauty marks the most northern extreme of the Ring of Fire. 75% of all the volcanoes in the United States are situated in Alaska, making it a perfect laboratory for volcanologists. The first step is to discover how the Ring of Fire's giant volcanoes form.
We're headed to Augustine Volcano, which lies in Cook Inlet, and it's part of the chain of volcanoes that extends all the way down into the Aleutian Islands.
It's a 60-mile journey out across the frigid Alaskan water. In the distance, the volcano soon appears.
There's the Augustine Volcano over there. It's going to be a perfect day to visit.
From high above the clouds, Dr. Bull can gain a clear view of the volcano's distinctive outline. Augustine is a stratovolcano, the type of volcano found all around the Ring of Fire.
Stratovolcanoes are quite unique in that they are shaped as beautiful cones, and Augustine is a perfect example of that.
Augustine last exploded in January 2006, the most recent of 7 eruptions here since 1935. Over the years, solidified lava flows have gradually built up on the volcano's flanks. To investigate what makes these volcanoes so dangerous, Dr. Bull climbs high up on the side of one of these lava flows.
This lava is made up of blocks. There's bits that are a little denser than others, and you can see there's a lot of different pieces to it. So we call this a blocky lava flow.
This blocky lava provides a crucial clue as to why the Ring of Fire volcanoes can be so deadly.
This lava is more thick when it comes out of the volcano, and its thickness will have an effect on how it runs down the slope. The thickness or viscosity of lavas can be shown in a number of ways. Hawaii lavas are quite runny. Honey is a perfect example of that. If you have the volcano putting out Hawaii-like lava, it's going to run quite easily down the rock. Whereas if you have something more like these blocky lavas, they're going to be a little bit more like peanut butter. They'll still run, but the viscosity is much greater.
The viscosity of lava is primarily determined by the amount of silica it contains. Silica is the most abundant mineral in Earth's crust.
The more silica, the thicker or more viscous a lava is likely to be.
Hawaiian lava contains little silica, so it's runny and produces a relatively flat landscape. But Ring of Fire lavas are rich in silica, making them sticky and less able to flow, creating tall, cone-shaped stratovolcanoes. During the 2006 eruption of Augustine, thermal imaging cameras were used to study the volcano. They showed this sticky lava building up layer upon layer. But the thickness of this lava also makes these volcanoes lethal.
Because these volcanoes have lava that is thick, things don't move through them very well. And bubbles of gases can build up.
Deep in the earth, under immense pressure, molten rock called magma contains dissolved gas. But as this magma rises, the pressure decreases. This drop in pressure means bubbles of the gas begin to appear, just like opening a bottle of soda. If the magma is runny, these gases can safely escape. But in sticky, silica-rich Ring of Fire magma, the gases can get trapped, often with terrible consequences.
It's like trying to have a bubble move through peanut butter. It won't happen quite so easily. So there's a lot of pressure that builds up. And once that pressure builds up, it reaches a point where it can't take all that pressure anymore.
The result? Giant explosions caused by the catastrophic buildup of gas inside the molten rock. This is the reason Ring of Fire volcanoes can be so dangerous. But it's not usually the initial explosion that kills. It's what happens next.
Those explosive eruptions can create plumes that go up for tens of miles.
When these plumes run out of energy, they can collapse back down the sides of the volcano in a superheated avalanche of ash and gas. With temperatures of 1,300 degrees Fahrenheit and speeds over 100 miles per hour, these flows destroy everything in their path. A terrifying consequence of the explosive eruptions caused by gases building up inside thick lava. In the next stage of her investigation, Dr. Bull searches for clues as to how this sticky lava forms. On Augustine's lower slopes, she hunts for lava samples from inside the volcano. This giant block of solidified sticky lava was once molten magma deep underground. It was blasted out here during an eruption, and it came with some intriguing evidence.
So what I'm seeing in this rock is a lot of minerals and a little bit in some cases of hornblende.
The presence of these hornblende crystals provides a crucial clue to how the magma formed.
This is important in telling us something about magma conditions where the hornblende crystallized. Hornblende is a mineral that only forms in the presence of water.
These hornblendes show water exists deep in the earth. Scientists suspect this water plays a crucial role in creating the magma that powers volcanoes. Deep underground, rocks are hot and semi-solid. It might seem that the presence of water would cool them down. But that's not what happens. This water, which is under huge pressure, alters the rock's structure and causes them to melt, forming plumes of magma. This molten rock soars up to the surface, building giant volcanoes. Without water causing magma formation deep underground, these Ring of Fire volcanoes would simply not exist.
A lot of this process we're still working on and we don't understand, but there's a fair amount of it that we do. And water has a very significant role in when and how rocks melt.
The investigation into why the Ring of Fire is so dangerous has uncovered two important pieces of evidence. Blocky lava flows are evidence of thick, viscous magma which traps gases inside volcanoes, leading to explosive eruptions. And hornblende crystals reveal that water deep underground encourages the formation of the magma that powers the volcanoes. The geology detectives figure out how this water gets underground and make a remarkable discovery: the chemical signature of microscopic organisms inside the volcanoes. All around the Ring of Fire, explosive magma is forming deep underground, fueled by water. Solving the mystery of where this water comes from is the key to how scientists will figure out why the Ring of Fire is so dangerous. The investigation now turns to Mount Lassen, an active volcano in Northern California. Surrounding the volcano are bubbling hot springs, boiling mud, and volcanic vents called fumaroles, belching superheated steam and gas. All this thermal activity is driven by the immense heat rising from magma deep underground. By sampling the gas coming from these fumaroles, scientists hope to discover the source of the water which causes the magma to form.
This device measures temperature. The temperature of this fumarole is 92.5 degrees C, about 200 degrees Fahrenheit. So just about at the boiling point for this elevation. And that's what we want for a good gas sample, a good boiling fumarole. So you can see what's happening at the surface here, all the steam coming out of the ground, but it's the gases that are along with this steam that we look at closely. And the composition of those gases tell us about what's happening at various depths beneath the ground where we can't see.
Tests on these gases, collected from volcanoes all around the Pacific Ring of Fire, have revealed something surprising. The gases contain carbon-12, a type of carbon that comes from living organisms. The specific levels of C12 found here are the unique signature of tiny sea organisms called phytoplankton. Billions of phytoplankton live in the ocean. As they grow, they absorb carbon-12 into their cells. When they die, they fall to the bottom, forming layers of sediment. In this way, their carbon-12 is transferred to the seafloor. Intriguingly, scientists have found this same carbon-12 pouring out of volcanoes all around the Ring of Fire.
Volcanoes of the Cascade Range have carbon dioxide that's very rich in carbon-12, and it's almost like you're cooking oceanic sediments that are rich in phytoplankton. down deep beneath these volcanoes to generate the carbon dioxide you see coming out the top. That links this carbon dioxide to organic sediments way offshore in the ocean. The organic matter that was originally phytoplankton becomes carbon dioxide that we see at the surface.
Seafloor sediments are getting into volcanoes, and these sediments contain seawater. This is the water that causes the rocks to melt below the volcanoes, forming magma. But a mystery remains. The magma plumes feeding the volcanoes lie sometimes hundreds of miles from the ocean. The scientists now have to figure out how the sediments loaded with seawater are moving so far inland.